Okay, so let's start. So last time we started with vorticity equation of the incompressible Euler equations, which I want to write down again. So vorticity equation. Omega is a vector field in R3. Its divergence 0 and satisfies dt omega plus u dot gradient omega is omega dot gradient u. And u is, you can be calculated by Biot-Savart law. At each moment of time, u at x is given by integral in R3 of this function, x minus y cubed, x minus y, cross product with omega ty dy. So last time we discussed the existence of the solution with some assumption on the initial vorticity. Okay? Say omega 0. Omega 0 belongs to the Felder spaces CK alpha R3 with some decay, which we can take to be L1. Okay. Here k is an integer starting from 0, and alpha is strictly between 0 and 1. Then there exists time and a unique solution, omega tx, which is ck alpha and L1 in the time interval. Okay. Okay, so before we proceed, I want to briefly discuss how to actually estimate the solution in the CK alpha norm. I didn't really discuss it last time. So also we can think of the iteration scheme that we introduced last time. How do we estimate the iteration scheme? But let's assume for simplicity that we already have a nice solution to the vorticity equation, and I will show you how we estimate this CK alpha. Okay. In reality, what we need to do is we estimate the CK alpha norm of the approximations and then take the limit. Okay. So estimating the Felder norm. Okay. So let's take k to be 0. Okay. It's the simplest case. Estimating C alpha norm. So what we need to do is we need to introduce the flow actually to do the C alpha estimate. So again, let's assume that we already have a nice solution to this vorticity equation. And the question is how fast the C alpha norm of vorticity will grow in time. Okay. So we need to recall that x is the flow of u, where u is the velocity of omega defined by this formula. So this means that by definition of flow, time derivative of x dx is u t x dx, and x at time 0 is little x. Okay. So what you do is you write this vorticity equation composed with capital X. So people say, just write the equation along the flow. That's what people say. So the point is that you compute this quantity, ddt. Now you see it's not a partial derivative because the point of this computation is that you consider little x, this one, as a fixed point and not a variable. Okay. So if you take the time derivative of this guy, okay, so it's just omega composed with the flow, capital X. Time derivative falls on this t, okay, which is just partial derivative of omega, but it also falls on this capital X. Then you need to use the chain rule. You first have derivative of omega with respect to this position, x, and then you take the time derivative of capital X. But by definition, that is just u. Okay? So if you do this computation carefully, what you get is exactly partial derivative of omega plus u dot gradient of omega. All of this evaluated at Tx. So the point is that for each t and x, we know that this equals omega dot gradient u. All of this evaluated at x. Okay, so we use this equation, time derivative of omega composed with x is omega times gradient u. We use this equation to estimate the CR. Okay, first observation is that here, basically, we can take the supremum in little x to estimate the change of maximum of omega in time. Okay. So the claim is that time derivative of omega maximum in R3 is bounded by, in absolute value, maximum of this. Okay. So it doesn't really matter that it's composed with capital X. Okay. It's a diffeomorphism of R3. So taking the maximum here is taking the maximum here. So you have this. And if you like, you can just write like this. Maybe with some constant. Okay. I hope this is reasonable. Another computation you can do here is you can also estimate the change in time of the L1 norm of omega. Okay. What you do is the following. You can integrate this equation in x. Small caveat is that you need to first take the absolute value and then integrate. There's some trick which I don't want to discuss now. Let's say we can just take the absolute value and integrate in x, little x. Okay. Then the point is that this capital X is volume preserving because U has zero divergence. So maybe I will write it somewhere else. So X viewed as a map from R3 to R3 for each fixed T is volume preserving. So the way we are using it here is simply that omega, so I will just write it like this. Omega composed with capital X integrated in R3, the little x is equal to omega dx, which is by definition the L1 norm of omega. Okay. So what's the point? Take the absolute value, integrate in little x, okay? You also then integrate the right-hand side in little x, and also in the right-hand side, this is volume preserving. So basically you get the same formula, same estimate. The change in time of the L1 norm of omega in absolute value, if you like, is bounded by omega dot gradient u in L1. So basically it has the same estimate. Okay, any questions? So the difficult part is to estimate this C alpha norm, which is by definition supremum of this different quotient. Okay. So how do we do this? So one way, probably the best way, is to do a bidirect brute force computation of the following quantity. So estimating the alpha dot. Okay. How do we do this? Take 2 points, x not equal to x prime in R3, and calculate the following. We don't really need absolute value here. You take the time derivative of this quantity. Okay. So what's going on here? For each fixed t, capital X is a diffeomorphism of R3. So this is exactly the C alpha semi-norm of omega at time t. Okay. So this is exactly semi-norm if you take supremum in x and x prime. And we are directly taking the time derivative of this. Okay, so we just calculate. The time derivative can fall here, in which case we get the time derivative of capital X, which is u. Okay. Or the time derivative can fall here, in which case you get the right-hand side. Okay. So it's actually not that complicated. So first of all, when the time derivative falls here in the numerator, what you get is, so I will introduce just simplifying notation, call this x prime. Okay. And then what we have here, we have omega dot gradient u at x minus omega dot gradient u at x prime. And there is another term, okay, which is, if you compute it carefully, looks like the following. X minus x prime, alpha plus 2. And you have this guy because it was not differentiated. And this is multiplied with u evaluated at x minus u evaluated at x prime, dot product with x minus x prime. Okay. So now what do we want to do? We can basically take the supremum over all little x and x prime, which are not equal to each other. Okay. In this expression, you see, this is basically calculating, this is bounded from above by the C alpha norm of omega gradient u. Okay. Now look at this. Here, you just give alpha power, which is just C alpha norm of omega, and you give two factors here. One factor cancels with this, x minus x prime, and there is still one factor which pairs with this to be bounded with the Lipschitz norm of u, or maximum of gradient of u. Okay. So the point is that if you carefully take the supremum in x and x prime, you get this inequality. This is bounded by the product in C alpha plus alpha times gradient u at infinity omega C alpha dot. Okay. So if you formally take alpha to be 0, you precisely recover this maximum estimate. Okay, and this is, you use the product rule bounded by alpha plus the other way at infinity omega C. Bounded by. And furthermore, this is trivially bounded by gradient of u in at infinity up to some constant. Okay. And one of the key estimates that I introduced to you last time is that this is bounded by C alpha of omega. That was the first key estimate, actually. This is bounded by some constant depending on alpha times omega in C alpha dot. Okay, so let me rewrite the estimate. Time derivative of omega C alpha dot is bounded by, in the end, some constant depending on alpha. So here it's important that alpha is between 0 and 1, strictly, times gradient of u in at infinity, omega C alpha dot. So here is a kind of small but important point. At this moment, we could have easily estimated like C alpha times C alpha. That's an easy estimate. But I intentionally used a slightly sharper estimate, which is at infinity times C alpha, in order to basically obtain the same estimate for C alpha, in the sense that the rate of change of C alpha is bounded from above by itself times gradient of u in at infinity. And you see the exact same quantity appears everywhere. So this is in some sense a proof of the well-known fact that for incompressible flows, if this quantity, gradient of u at infinity, is bounded, it controls everything. And what is probably slightly surprising is that the same holds for every ck alpha, even if k is super large. Okay. So this quantity controls everything, controls C infinity of omega. So, any questions? Sorry? Gradient of u, in that case, is also in ck alpha. Is that? Yes, that is true. But the point is that even if you change this to ck alpha, the constant would change, but you have the same estimate. Yes. But this I will not show. It's just some computation. You do it as an induction in K. Okay. Now what I want to show you is, last time I told you this Beer-Kato-Maeda criterion, which says that actually omega in at infinity, the maximum of the vorticity, controls ck alpha. Okay. And that uses another key inequality that I showed you last time. And let me apply that directly here. Okay, so let's just work with C alpha norm, k equal to 0. So let's recall that this is bounded by Okay, so before doing that, I'm sorry, we can rewrite this estimate slightly as follows. Time derivative of log of omega c dot alpha is bounded by c alpha gradient u. Okay. This is the same. I hope so. Okay. But the point is that all the other quantities satisfy the same inequality. So we can basically replace this with at infinity and also with L1. So why do I want to write this in this form? Because last time, the third key estimate was an inequality for this term, which was in the form omega in at infinity times another constant, which I observe here, okay, 1 plus 1 over alpha times log of this thing, omega at infinity, 1 plus alpha, and omega L1 alpha over 3, omega c dot alpha with power 1. Maybe it's alpha here. Sorry. We will prove a similar estimate today. Okay. So here we have this quantity. Okay. Let's call this, I don't know, d of t. And what is this estimate here? So d is inside log. Okay. We can estimate, because we have this also for at infinity and L1, we can estimate log of dt, time derivative, is bounded by some constant omega at infinity, 1 plus 1 over alpha, log d. Sorry, maybe it's a bit complicated, but now in the right-hand side, you only see the maximum of omega, nothing else. If our initial vorticity is C alpha and L1, D is finite at time 0, okay? Unless omega is identically 0. And if omega in at infinity remains finite, from this inequality, you see that d of t, first log of d of t remains finite. Okay. So d of t remains finite because log of d remains finite. So d of t is finite. This is d of t. We assume that this remains finite. So this remains finite. That's how we conclude omega in C alpha and L1 remains finite. Okay, any questions? Yes, you need to basically Yes. So let's say this is d of t. You take the log. What is this? You can change product inside log into a sum. That's all we do. It's like this. And funny thing is that here we have minus of at infinity with some constant, maybe 1 plus alpha. Okay? And we take the time derivative of this entire thing in absolute value. This is why I kept these stupid absolute values all the time, because we need it here. Okay? So all of this is estimated by this. Yes. Thank you very much for the clarifying case. Yes, coefficient depends on alpha, but it's not so important because alpha is between 0 and 1. Yes. Okay, so I think this is all I want to talk about. How do we actually estimate the solution? And again, strictly speaking, what you need to do is you do these estimates for the approximating sequence of solutions denoted by omega n. And then you take the limit. And the estimates are carried over in the limit. There is another issue which I didn't discuss last time, and that is uniqueness. Uniqueness issue. Okay. And related to this uniqueness issue, one student yesterday asked a very nice question, which is, if omega is just C alpha, okay, k equals 0 case, the derivative is not defined, strictly speaking. It's okay when k is at least 1. So when k is 0, omega needs to be interpreted as a distributional solution to the vorticity equation. Okay. On the other hand, if you look at this equation, which is the equation along the flow, this equation does not have any derivative on omega. Okay. And you can show that at this regularity, distribution solutions of this are equivalent with solutions to this, which does not require omega to be differentiable. Okay. So this is a slightly delicate point, which also enters if you want to prove uniqueness of solutions. I think you cannot prove directly uniqueness from the vorticity equation when k is 0. This is slightly annoying. This is slightly annoying. There are two ways, at least two ways, how to get uniqueness in this case. One way is to use the velocity equation again. Okay. This is actually the usual way people prove uniqueness. What I mean is the following. Let's say you have a solution to the vorticity equation with C alpha vorticity, and then you can prove that with U defined by this formula, U satisfies the velocity equation. Okay. and the velocity is Lipschitz. Gradient of velocity is bounded. And in the level of the velocity equation, you assume that there are two solutions, two different velocities. Okay? Take the difference and do some LP estimate for the difference of velocities. Okay? That's the usual way people prove uniqueness. And again, you cannot do this directly here because you imagine there are two solutions, omega 1 and omega 2. Take the difference of the solutions. And if you try to do some LP estimate for the difference, you will get a term where gradient of omega appears in the LP estimate. But for our solutions, gradient of omega is not in LP for any P. This is only a distribution. So uniqueness, unfortunately, you cannot do it here. Okay. Then maybe it's very annoying that you have to use the velocity equation because the whole point of the vorticity equation is that you do not want to use the velocity equation in some sense. So there is actually another way of getting uniqueness, which is to use the Lagrangian formulation of the equation. That's also not that quick, but let me briefly mention the Lagrangian formulation, and then we can move on. Okay? The Lagrangian formulation. So I'm discussing this because I think it's kind of interesting in its own. So what is Lagrangian formulation? So the vorticity formulation, what was the purpose? Is to rewrite the equation completely in terms of the vorticity. Okay, that was vorticity formulation. Lagrangian formulation idea is very simple. Write the equation completely in terms of capital X. And you can prove existence and uniqueness directly from the Lagrangian formulation. So let me quickly derive the Lagrangian formulation. Again, maybe now this is clear to everybody. This is definition of the flow. Okay? But here we use the Biot-Savart law. The Biot-Savart law, now I'm lazy, so I will just write it as some kernel K at X minus Y, cross product with omega Ty dy, okay? So K is the function over there, except that we want to evaluate at the flow. Okay. But we do not know this at this moment. Okay. So to close a formulation, we want to remove this. Here is where the Cauchy formula enters. First, what you do is you change variables. You change y into capital X of t, z, say. Okay. This is measure preserving transformation. So what you get is you get So I will just write here directly minus x tz x tz dz. Okay. But I told you the Cauchy formula for this last time. Okay. So using the Cauchy formula, what you get is the following. Time derivative of capital X dx equals integral in R3 k at x dx minus x tz times gradient x tz omega 0 z dz. And we know the initial condition x 0x is x. And this is the so-called Lagrangian formulation of the incompressible Euler equations. Because now the only input in this equation is omega 0, which is given to us. We know what this is, okay, because it's given. K is a given function written over there. So this is purely an integral differential equation for capital X. It's the only unknown. So you can use this formulation to prove existence and uniqueness with CK alpha vorticity. So the point is that if you have two solutions, you can estimate the difference using difference in vorticities. Okay? So if x and say x tilde are solutions with initial vorticity, say omega 0 and omega 0 tilde. Okay? So say this is a solution to this vorticity, this is solution to this vorticity, then you can close an estimate of the form x tx minus x tilde tx in C1 alpha is bounded by some constant depending on alpha. Alpha is between 0 and 1. Supremum for time between 0 and t. The difference of vorticities, okay, here we can just write difference of vorticities at the initial time. Okay. Maybe with L1, sorry. And this is a long proof. Okay. This proof is kind of similar to estimates that I will show you, which is estimate for this velocity gradient. This estimate is kind of similar. But what's the point? The point is that now, if we have the same initial data, they have the same flow. They have the same flow, so they have the same velocities. Vorticity is curl of the velocity, so they have the same vorticity. That's it. But of course, this is a very hard estimate, which is in the book of Maeda and Bertozzi. Okay, any questions? So now let's go to the concept of singularity directly. So what I will do is I first introduce the concept of self-similar singularity and then go to a toy model in which self-similar singularity can be easily proved. Then I will come back to the Euler equations. Okay. So the question here, the main question here is whether this capital T can become infinite, or is there a time at which the solution becomes infinite? This is called singularity or blow up. Okay. So it turns out that in many of the partial differential equations, which becomes singular, okay, often the singularity is self-similar form. So I will define what it means. So self-similar singularity let's say just SSS, okay? So you can define this concept for any PDE, which depends on time, okay? And let me just write it directly for the vorticity equation, okay? So here is kind of definition. If there exists a lambda and f, a lambda are parameters, just real numbers, and f is a function, okay? If there exists a lambda and f such that one over t star minus t to power a, capital F, x divided by t star minus t to power lambda. If this, say this is omega t, comma x, solves the vorticity equation, say star, then we say it is a self-similar singularity. But let's assume that A is positive. We want to have that A is positive. I'm sorry. Let's say A and lambda are both positive, and F is not identically equal to 0. Okay. These assumptions can be relaxed, but I do not want to discuss all the possible cases. Okay. Yes, question? That's a very good question. I don't have a good answer. It just turns out that most singularities that we see are self-similar. There are some singularities that are not self-similar, but usually they are unstable singularities, so that you will not observe it in real life. But I do not have a good answer why the singularities we see are self-similar. It's kind of how our universe works. Okay. There is no general result like that. It's probably, I don't know, very difficult or even false. So first of all, I'm sorry, so T star, okay. Let's say T star is also positive. It doesn't really matter because our equation has translation invariance in T. Okay? So why is it called a singularity? First of all, it's simply because if A is positive, okay, and T increases from 0 to capital T star, assuming that it is positive, okay, this will become infinity. Okay. This will become infinity. So we expect omega, the value of omega, as time approaches T star, to become infinity. Okay? So that explains the word singularity. Okay? And why it's called self-similar. So you can see this as some self-similarity in graphs. Okay? So this formula tells us that if you consider the graph of the solution at different moments of time, they are similar to each other in shape. So maybe I will become more precise. In a toy model that I will show you, okay, what happens is that if the initial data looks like this, okay, this is initial data, the solution, as it approaches T star, behaves like this. And it becomes sharper and sharper. Okay. So it's important to notice that there are two transformations here. So this one is easy to understand. This one is easy to understand. This is just making the function very large. Okay? But this is independent of x. This is just making the graph large by some factor, which becomes infinity. So this is easy to understand. Now, what is this? This is zooming in or zooming out, depending on whether lambda is positive or negative. For simplicity, I will assume lambda is positive. It means that as t approaches T star, we are zooming in. So again, if you have initial data like this, what this does is, first, it makes the function very large. That's this factor. The second factor is you rescale the x variable, and it zooms in like this, or zoom out, depending on the way. So the function becomes sharper and sharper. In other words, okay, so this is kind of stupid rewriting, but I think it's useful. In other words, instead you can rescale this x. Okay? If you instead write this here and multiply by t star minus t to a, okay, this is f of x. It's the same thing, okay? Same thing, which is maybe hopefully makes more sense. You have your solution, omega, depending on time. For each time, you zoom in, and you make it now smaller, okay? You make it smaller, then it is independent of time. It's function of x only. And now this is really a better, I don't know, definition, because there is something important which I want to discuss is asymptotic self-similar singularity. Let me call ASS. Okay, the definition is simply that this converges as t goes to t star locally in space. Okay. So the singularities that we see will be usually not exactly self-similar. There is always some error. But how do you make precise the meaning that the solution is almost self-similar? This is one way. This is one way. Okay. So I hope you can try to understand it from graphical point of view. Okay. You have a solution. You have a solution which is becoming infinite at some time t star. Okay. But what you do to this solution becoming infinite is you multiply by some time-dependent number, and also you zoom in. You zoom in closer and closer to the point where the function becomes infinite. Then, at the time of singularity, you converge to some nice function. That is the meaning of asymptotic self-similar singularity. Okay, any questions? So these are just definitions. And here comes the theorem of Tarek-Elgindi. Okay, the theorem. And also Elgindi, Gur, Masmoudi. So in the paper of Tarek-Elgindi, he proved that there exists actually exact self-similar singularity for the vorticity equation. So for alpha positive but sufficiently small, there exists exact self-similar singularity with omega 0, the initial data, which is just you plug in t equals 0 there, belongs to C alpha R3. The second result, which is contained in this paper, the second paper, is that they proved in some sense that this self-similar singularity is stable in some sense, which I will not describe here. So here one issue is that this exact self-similar solution decay very slowly at infinity. Okay? That's one issue. While in our existence theorem, we assumed quite fast decay at infinity. So we, strictly speaking, do not need this much decay, but this exact solution decays really slowly, really slowly. So for this issue, they proved in this paper that there exists initial data, C alpha. Among other things, it can be compactly supported in space, so the best decay possible, such that solution with this data is asymptotically self-similar singularity with this profile F. Okay. So in some sense, the second result removes the potential criticism that this solution does not decay at infinity. Okay, so any questions about the concept of self-similar singularity or the theorem here? First one? Oh, no. The statement is that there exists a solution like this. And then you plug in t equals 0 and you get whatever is in the left-hand side. It's a very special initial data. But then the second result is that you can basically make that data compactly supported, and the behavior is asymptotically the same at the singularity time. That's a very important part. I hope to discuss it tomorrow, maybe. Yes.
What is the convergence?
That's a great point. It depends highly on the equation that you consider. But usually, we want at least in C0 sense. Because in this equation, singularity is at infinity. Yes. Yeah, that's a very good point. This convergence, it really is equation dependent. But mainly you want to make sure that it's a blow up for your solution if you have this convergence. Okay. So from now, what I will do is I will actually go to a toy model, which you can consider as a very simplified equation of the vorticity equation, and do the estimates, including self-similar singularity for the toy model, and come back to the Euler equations. That's actually how Tarek ended up with this result. So before I introduce you the model, let me first discuss the Hilbert transform and also the Zygmund inverse. And Hilbert transform. In the real line. Okay. So the Zygmund inverse operator I write as capital lambda inverse. Okay. It applied to a function defined on the real line is defined by this integral 1 over pi integral in R log absolute value x minus y fy dy. This is inverse of what is called the Zygmund operator, but that's not so important. I just want to introduce to you this operator. Okay. And the Hilbert transform is just the derivative in x of this operator. Okay. So Hilbert transform of f, by definition, is just derivative, dx, of Zygmund inverse of f, which is formally, if you differentiate the log, you get integral of 1 over x minus y fy dy. But this is incorrect because this is not a locally integrable function in R. Okay. So strictly speaking, if you just write this, it's incorrect. It doesn't have a meaning because this is not locally integrable. The precise thing is you just write a phrase PV. It's called principal value integration, and it's defined precisely by the formula limit epsilon goes to 0, and you integrate only in the region of y, where x minus y is greater than epsilon, and then this is okay, and then you take the limit. Okay. So this limit is definition of PV. So I want to, any questions? Yes? Yes, let's say f is smooth for now. Yes, that's a very good question. Any other questions? So there is something to be proved here, okay? Which is, so this is a well-defined function if f decays at infinity, because this is a integrable function locally. Okay? The claim is that if you differentiate this function, you get this. Okay? So the derivation is not that hard, and it assumes that f is differentiable. So what do? You can change variables in a way that instead of y here, you have x minus y. So you can just change variables to write the transform as this. But now when you differentiate outside the integral, it comes here because the resulting integrand is still locally integrable. So in real analysis, so this is very important lesson from real analysis. When can you change derivative with integral? You can do it only when the resulting ddx of this is L1, at least locally. Yes, exactly. So this is okay if f is differentiable. So you have this. This is a well-defined integral. But now what do you want to do? This is same as df dy with a minus. Yes? Because the variable is x minus y. And then you want to move dy to log because it's integral in dy. So the point is that you cannot move. You just move carefully. That's it. Maybe it sounds very stupid, but that's what the principal value integral is. So again, this is well-defined integral. That means this equals the limit as epsilon goes to infinity to the region y such that x minus y is greater than epsilon. Okay? Because it's a well-defined integral. But now in this integral region, you can move because here derivative of log is okay. Thank you. Thank you. Thank you. Yes, so you do it and you get 1 over y with plus, because you moved the derivative, modulo the boundary terms. What are these boundary terms? So here you will have epsilon, okay? Sorry, log. Thank you very much. Log of epsilon. And you have the values of f on the boundaries. F, x. Sorry, I messed the sign. Maybe something like this or with minus. Okay. It's something like this. So if f is differentiable with bounded derivative, this is order epsilon. And the limit is still here, everywhere. So if f is ellipsis continuous, then this is order epsilon, which goes to 0 even after multiplying by log. Right? No? Maybe not. That's how you end up with this, which is after another change of variables equal to this again. Okay, so this is the definition of the Hilbert transform. So a small point is that although in this derivation of the formula, we use that f is basically Lipschitz function, but after deriving this formula, we can extend the domain of definition of Hilbert transform by a density argument as long as we can estimate the Hilbert transform in a larger space. Okay? So that's how the story goes. It's the same for Fourier transform. Initially, we define Fourier transform for L1 functions, maybe with other assumptions, but then we estimate that Fourier transform in different function spaces, and then we can extend the domain of definition of the Fourier transform. And the same goes for the Hilbert transform. Okay, any questions? So for the Hilbert transform, I'm going to show you the key estimates, which are completely parallel to the estimates for the velocity gradient. Okay. So important point here is that Hilbert transform is called an example of the singular integral operator because this integrand here is singular in the sense that it's not integrable. But it's barely not integrable. Okay? And Hilbert transform is also order 0 operator. What does it mean? So Hilbert transform H is of order 0. And this will be important in what follows. So what's the concept of order? If you have linear operator, say T, okay, T is a linear operator, you apply to T a rescaled function, f of lambda x, lambda say positive, okay? If this equals, if this equals lambda to power sigma of TF at lambda x for every lambda and every nice function f in the domain of T, then we say sigma is the order of T. Okay. So what is the claim here? So it's an important computation to do is that Hilbert transform is order 0 by definition if you apply the Hilbert transform to a rescaled function f of lambda x. This equals Hilbert transform of f evaluated at lambda x. This might be confusing, but it's okay. It's confusing. And you can probably already imagine why that concept of order is fundamental in self-similar singularity. Because here the key point is to understand how these functions scale when we rescale the independent variable. And Hilbert transform is order 0. Okay? So simpler examples, derivative is order 1. Derivative is order 1. I want you to see it immediately. If you differentiate not f, but f rescaled by lambda, this is just chain rule. It's lambda times derivative of f at lambda x. Okay. So order of derivative is 1. If you have integral, say taking antiderivative, order will be -1 in 1D. Okay. Okay, so slightly more interesting example is that here we have the Biot-Savart law. Okay. We see this as an operator. Input is omega, output is u. Okay. This linear operator has order -1. Okay. So that's a computation to do. So the Biot-Savart law is order -1. And I told you that differentiation is order 1. You can compose operators. So this is order 0, yes. Like the Hilbert transform. Again, what's the meaning of this? If you calculate gradient of u of rescaled omega. So here I'm abusing notation. This means gradient of u of this rescaled omega that equals gradient of u of omega evaluated at lambda x. Just like the Hilbert transform. Okay. So let me just conclude with the observation that the Hilbert transform is actually order 0. Okay. It's okay. So what do? We calculate the Hilbert transform of f rescaled. Let's calculate this. Okay. So by definition, we just put lambda y here. Okay. Is that correct? And we want to show that this equals, want to show Hilbert transform of f at lambda x. So I hope it's correct. What is this? By definition, it's 1 over pi pv 1 over lambda x minus y fy dy. This is just definition. What do? Now you change variables. Let's say y is lambda y bar. Okay. dy is lambda dy bar. So you continue pv 1 over, now you can see lambda x minus lambda y bar. So you can factor out lambda x minus y bar and f lambda y bar dy bar with lambda. So they cancel. And you see this is equal to this. Okay. Okay, I will stop here and tomorrow I first want to discuss some properties of the Hilbert transform. And the point being that such proofs with very small changes can be applied to estimate the key estimates that I stated for gradient of U. Okay, that's it for today.